Halo. Dobrý večer. Zdravím všechny posluchače tady v aule Slezské univerzity a zdravím naše diváky na kanále Dobré vědět. Stále čekáme na to, až se pan doktor Zubrin přihlásí s online streamem přes platformu Zoom. Takže prosím o chvilku strpení. Tady máte aspoň důkaz, že jde skutečně o živý stream přímo se samotným Robertem Zubrinem. Pokud se nepřipojí do během pár minut, zkusíme rychle vymyslet nějaký náhradní program.
Hello. I can. Can you hear me? Can you hear? Can you hear?
Chtěl bych vás přivítat tady na půdě Slezské univerzity při mimořádné příležitosti tady u nás v Czech Mars Society. Naše skupina malá se začala scházet přibližně před 3 lety, aby se vzájemně informovala o pokrocích na poli dobývání
Can you hear
vesmíru.
me? Please answer.
Krátce na to nám bylo naznačeno, že takovouto událost si nemůžeme nechávat jen tak pro sebe, a tak začaly naše veřejné schůzky, na kterých jsme dělali hlavně populární přednášky a byly přenášeny přes kanál Dobré vědět. Tato naše činnost vyvrcholila 11. dubna, kdy jsme byli přijati nebo uznáni jako odnož celosvětové Mars Society. Při této příležitosti její prezident doktor Zubrin přislíbil přednášku na téhleté naší akci. Takže přeji vám velice příjemný zážitek a předávám slovo Petru Blažkovi, který představí našeho dnešního řečníka. Prosím, Petře.
Thank you. So now this is the end of Czech part, and the rest of the talk will be in English, or in my case, the combination of the two languages. And so, ladies and gentlemen, distinguished guests and esteemed members of the audience, it is my great pleasure to introduce you to Dr. Robert Zubrin, an American aerospace engineer, writer, innovator, and founder of the Mars Society. One of his most notable contributions is the groundbreaking proposal known as the Mars Direct, which outlines a cost-effective and achievable method for sending humans to Mars and establishing a sustainable colony on its surface. Dr. Zubrin is also a masterful communicator and writer. Through his numerous articles and books, including the critically acclaimed The Case for Mars, which you can see here, and other books are on display. He has eloquently articulated the scientific, technological, and philosophical reasons why humanity must strive for a multiplanetary existence. As the founder and president of the Mars Society, he has nurtured a global community of scientists, engineers, and enthusiasts like us here, who share his passion for space exploration. He, recognized for his outstanding contributions, Robert Zubrin has received numerous honors. For example, the prestigious Heinlein Prize for Advance in Space Commercialization. And this is an interesting prize. Since 1988-89, only 18 people received this honor, including such names like Elon Musk, Freeman Dyson, Stephen Hawking, Arthur C. Clarke, Werner von Braun even, and more. So, ladies and gentlemen, please join me in welcoming a true champion of Mars, Dr. Robert Zubrin. So please, sir, the floor is yours.
Well, thank you. How to say thank you in Czech? Děkuju, something like that. Hi. It's my pleasure to be able to talk to you. And I want to thank you for your interest in coming and for your interest in the subject of expanding humanity into the solar system and beyond, because I think that this is the most important thing going on in the world at this time. That is, there's all sorts of things going on in the world right now, and some are important, like the war in Ukraine, and some are not important, such as many other things that fill the newspaper. But 500 years from now, this is what is going to be remembered for this time. I'm an American. If you ask any American what happened in 1492, they will tell you that Columbus sailed and found America. They will not know about any of the other things that happened in the year 1492, and there were many. England and France signed a peace treaty in 1492. The Borgias took over the papacy. Many other noteworthy events happened that were important at the time but are not remembered today. But humans to Mars will be remembered 500 years from now. Now, can I show charts, or is that not possible? Okay. All right. So, let's see. So, can you see me or just the chart? You see both? It's good. All right. So, okay, we don't need stuff like this to go to Mars. This is one concept of a giant nuclear electric ion drive spaceship to go to Mars. And if indeed this was needed to go to Mars, we're not going in 10 years. We're not going in our lifetime. This thing looks like an Imperial Star Destroyer from Star Wars. But this is not an image of a plan to go to Mars. This is an image of a plan to realize the science fiction spaceship. But we don't need science fiction spaceships to go to Mars. There are people who say we need to establish a base on the moon before we go to Mars in order to practice Mars exploration before we go. Now, we should practice Mars exploration before we go, but we can do it on Earth. The Mars Society, in fact, has a base in the Arctic and one in the American desert where we can practice Mars expeditions on Earth. And we should, but we don't need to hold up a Mars mission until we spend 20 years on the moon. What we do need to go to Mars is a heavy lift. And in fact, we have it. We had it 50 years ago with the Saturn V. We have it again right now with the SLS. And very shortly, we're going to have it, I believe, with Starship, which is a fully reusable heavy lift vehicle, capability in the Saturn V class. But because it's reusable, will cost at most 5% as much as a Saturn V launch to launch. But if you have a heavy lift vehicle of whatever design, this is how you can do a human Mars mission. This is the Mars Direct Plan. You have a heavy lift vehicle. And in the first year of operations, we do one launch of the heavy lift vehicle, and we use it to shoot off to Mars an automated payload weighing around 40 metric tons. And this payload flies out to Mars on a minimum energy trajectory. It will take 8 months to do it. And then it uses an aeroshell to capture into Mars orbit and then come into the atmosphere. The aeroshell takes you to subsonic speeds, and then we pop a parachute, and then we finally land with rockets, just like we did, frankly, with the Viking mission in 1976. Now, what is this that we have landed on Mars? The payload consists of a number of things, of which the primary object is a Earth Return Vehicle, or ERV. This is a little spaceship for traveling from Mars back to Earth. It has a small cabin around 5.6 meters tall and 5 meters in diameter. It has sufficient accommodations for a crew of 4 people for a 6-month voyage from Mars to Earth in the final stage of the mission. However, no one is in it now. Then slung below the cabin, not shown in this, below the cabin, we have 2 methane oxygen rocket propulsion stages, but they're not filled with propellant. If they were, this would weigh 4 times as much as it actually does. What we do have in the lower stage tanks are about 6 tons of liquid hydrogen. And then slung below the vehicle, not shown in this diagram, we have a rover, a roving, like a small pickup truck that runs on a methane oxygen engine. And in the back of that truck, we have a small nuclear reactor with a power of 100 kilowatts. Now, after we land, we telerobotically drive the truck 100, 200 meters away from the landing site, and we put the reactor down on the ground, preferably in a depression in the terrain, like a crater or just on the reverse side of a hill. Anything to put a large amount of dirt shielding between the reactor and the main landing area. And then we turn the reactor on, and now we have power at the ship. And what we do then is we run a pump, and we acquire Martian air, which is mostly carbon dioxide gas, CO2. We can react hydrogen with carbon dioxide in the presence of a catalyst and it will produce methane, CH4, and water, H2O. Methane is our fuel. The water we take and we split into hydrogen and oxygen. The oxygen is the oxidizer. The hydrogen we recycle to make more methane. And then to get the right amount of oxygen, we run a third reactor in which we take carbon dioxide and we split it into carbon monoxide and oxygen. The oxygen we keep is useful oxidizer for the rocket. The carbon monoxide we vent as waste. And what we managed to do is we've turned 6 tons of hydrogen that we brought from Earth into 108 tons of methane oxygen rocket propellant on the surface of Mars. So we've expanded the amount of propellant we've brought to Mars by almost a factor of 20. And that's what makes this mission work. It's like a hunter living off the land, only needing to bring his bullets and cartridges, but acquiring the useful mass of a bison or an elk or some other large animal that he can use for food. Travel light, live off the land. That is the philosophy of Mars Direct. And in fact, only about 96 tons of the propellant that we made is needed for the Earth return vehicle. There's about 12 extra tons, and they can be used to power ground vehicles to explore Mars. And that's very important. The chemically propelled vehicles have a much higher power to mass ratio than you can get with electric vehicles. And so that's why they're much more popular on Earth. And we really want them to explore Mars. So the ability to make propellant on Mars is key, not only to making the mission cheap, but to making it effective, which is equally important, because there's no point going to Mars unless you can do something effective when you get there. We're going to Mars to explore. The key requirement is mobility, and the ability to make propellant on Mars will give us mobility. I've built systems that do exactly this chemical synthesis. And in fact, people have built systems that do this chemical synthesis for over 100 years. It's not a magic trick. It's actually 19th century industrial chemistry. So now it took 8 months for the Earth return vehicle to fly to Mars. It took 10 months to make the propellant. That's 18 months. There's 26 months between launch windows from Earth to Mars. So well before the next launch window has opened up, we will know we have a fully fueled Earth return vehicle sitting, waiting for us on Mars. And that being the case, at the next launch window, we can launch 2 more rockets. One shoots out another Earth return vehicle with no one in it, but the other shoots out a Habitat spacecraft with a crew of 4 astronauts in it. Now, because we have our return ride waiting for us on the surface of Mars, we don't need to fly to Mars in some fantastic Imperial Star Destroyer spaceship. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. No, we can fly to Mars in a tuna can. And that is very fortunate because we know how to make tuna cans. Now, this is larger than the tuna can at the grocery store. It's about 8 meters in diameter, and the barrel section is about 6 meters tall. So it's got 2 decks, each with 3 meters of headroom. Okay. The upper deck is where the people really live. The lower deck is more of a garage, cargo hold, workshop kind of place. Here is one potential layout of the upper deck of the HAB. And what you can see are 4 little staterooms for each of the 4 astronauts. There's a bathroom, there's a science room, there's an exercise room, there's a galley kitchen. People eat and probably actually spend most of their time, little table. And then in the center, the circular center, is a solar flare storm shelter. Okay. Now, this is worth talking about a little bit. There's 2 kinds of radiation that can harm you in interplanetary space. There's solar flares and there's cosmic rays. And these are very different from each other. Okay. Solar flares come from the sun. They come unpredictably. You might get a big one about once a year, but you could have two in the same month and then nothing for 3 years. You have more likely to have them during solar max than solar min, but they could happen anytime. But has a probability about once a year. Now, and in a few hours, they can deliver over 1,000 rems, 10 sieverts of radiation, which is enough to kill, either immediately or after a brief period of radiation sickness. That's the bad news. The good news, however, is the kind of radiation that solar flares are made of are protons with energies of about 1 million volts. And those can be stopped by 10 centimeters of water shielding, or things that from the nuclear point of view are essentially the same thing as water, such as food or metabolic wastes that are produced from water and food. And we have enough of that material on board the ship in the way of provisions for the crew that we can pack it in around this center circular area and shield it against solar flares pretty well. So if a solar flare happens, the alarm bell rings, the crew goes into the shelter, and they stay there packed together for a few hours, and then all clear rings, they come out, it's over. Okay? So that's how you're safe against solar flares. Now, the other kind of radiation in space are cosmic rays. Now, cosmic rays do not come from the sun. They come from interstellar space, and we actually don't really understand the process that produces them. But they do come, and they have energies not of 1 million volts each, but of 1 billion volts each, 1,000 million volts each. And so you can't stop them with 10 centimeters of water. They'll shoot right through that. Okay? On Earth, we're protected by our atmosphere, which is the equivalent of 10 meters of water of shielding. And 5 meters would do, but we can't have that much shielding on a Mars ship. It would weigh too much. So you're going to take the dose. However, the good news is that the dose is not that large. It's about 50 rems, half a sievert of radiation dose during the whole 2.5-year Mars mission. Okay, so it's not a quick dose. It's spread out over time. And in fact, half a sievert over that period of time would not produce any symptoms at all. If you took half a sievert in 1 hour, that would produce radiation sickness, although it probably wouldn't kill you. But spread out over 2.5 years, it's like drinking a glass of wine, a day for 2.5 years. There are no effects. If you had 1,000 glasses of wine in one night, it would kill you, but one a day does not. Okay. So it's believed, however, that unlike wine, this would increase your statistical risk of getting cancer by about 0.5%, which is actually a modest portion of the overall mission risk. In fact, I don't know what the statistics are in Czech Republic, but in the United States, the average person who does not smoke has a 20% risk of dying of cancer, and the average smoker has a 40% risk. Okay, so in fact, there's a 20% risk of smoking of cancer. This is 0.5%. It's much smaller than smoking as a risk factor. So in fact, if you recruited the crew out of smokers and sent them to Mars without tobacco, you would be reducing their chance of getting cancer. So one reason to send people to Mars might be for their health. Now, the other thing is, so while people talk a great deal about the radiation danger in space, in fact, there have been a fairly large group of astronauts and cosmonauts who've spent enough time on the space station to get the same kind of radiation dose as we're talking about. And there have been no radiological symptoms observed on them at all. Okay, hasn't been observed. However, there is another health effect that we have observed in space, and it's not from radiation. It's from zero gravity. Okay, zero gravity weakens people. It weakens your muscles. It weakens your bones. Okay, now if you have a very strenuous exercise program, about 2 hours a day of working out, you can overcome that. But many astronauts don't do that. And so when they come down after they land, it's a couple of weeks before they're ready to do very much on Earth. And we don't want that, because we want our astronauts in good physical shape to explore. So I believe we should provide artificial gravity for the spacecraft. And the way you can provide artificial gravity is by using rotation. So here is on the left is the upper stage of the booster that threw the spacecraft to Mars. And then on the right is the spacecraft. And we are connected by a tether of about 1.5 kilometers, 1,500 meters. And if we spin this up at 1 RPM, 1 revolution per minute, this will create Mars gravity in the habitat. If we spin it at a little less than 2 RPM, we can create Earth gravity in the habitat. And this will avoid the health effects of zero gravity exposure. So we have been flying to Mars on a 6-month trajectory. The 8-month trajectory is minimum energy. That's the minimum amount of propellant we'll send you to Mars with 8 months. But it doesn't take too much more to get you there in 6. If you start trying to go faster than 6, then the propellant, it's exponential. It starts impacting your mission. But we can get there in 6 without too much impact on the mission. And also 6-month trajectory is actually a very good trajectory to go to Mars in, because it's the free return trajectory. That is, if you head to Mars on a 6-month trajectory and you decide not to go to Mars, you can fly past Mars. You'll go out into the inner asteroid belt, about 2 astronomical units away from the sun, and you'll loop around and you'll come back to Earth's orbital distance from the sun exactly 2 years after you left. So the Earth will be there. Okay. If you tried to go to Mars faster than 6 months, you would loop out further and you'd come back more than 2 years after you left, and you would miss the Earth. So, in fact, I believe the 6-month trajectory is the best trajectory to go to Mars, because it gives you the free return. If I had a superior propulsion system like a nuclear thermal rocket, I would not use it to go to Mars faster. I would just use it to increase the spacecraft payload. Okay, but still go to Mars in 6 months. Now, 6 months is longer than people today are used to travel places, but it's the standard rotation on the International Space Station. It's about how long it took to sail from England to Australia in the 1800s. It's certainly something that people can manage. So we take 6 months to go to Mars. And then we're going to be on Mars for 1.5 years, and then the window opens and it'll be 6 months back. So we'll be away from Earth for 2.5 years. 6 months back, out, 6 months back, 1.5 years on the surface. Anyway, we go to Mars, we get close, we fire a pyrotechnic, which cuts the cable, and now we aerobrake into Mars orbit, and then we go and land at the first landing site where the fully fueled Earth return vehicle is waiting for us. Now, that's been there for 2.5 years. It has explored the area with rovers to identify any landing hazards. It has put a radar beacon on the ground, just like one at an airport on Earth. We have an expert pilot piloting the HAB. We should be able to land exactly on the spot. And if you know your space history, you may know that even during the Apollo program in 1970, we landed an Apollo lunar lander within 200 meters of a Surveyor robotic probe that had been sent to the moon a few years before that. And we have much better guidance systems today. So we should be able to land accurately. But if something goes wrong and we land 100 kilometers away from the landing site, we're still okay. Even 300 kilometers away, we're still okay. Because we have with us in the lower deck of the habitat a pressurized ground roving vehicle, like a small sports utility vehicle, runs on a methane oxygen engine, and it has a one-way range of 1,000 kilometers. So it would take extremely bad piloting to land outside of its reach. But let's say even that goes wrong. We land on the wrong side of the planet. Well, in that case, we can still save the mission by taking the second Earth return vehicle, which is following us out to Mars. It is on an 8-month trajectory. We would bring it down to land near us wherever we did land. Now, in that case, we would be depending upon the propellant making to work in real time instead of in prior time, before time. But this is a third level mission backup. And finally, as a fourth level backup on the mission, if it all goes wrong, everything goes wrong, if we can't land accurately, if we can't drive to the Earth return vehicle, if we can't use the second Earth return vehicle, the backup is we have enough supplies with us to last for 3 years so that we can just last on the surface of Mars until the next launch window opens and more supplies and another Earth return vehicle can be sent out to us. So we have a 4-layer defense in depth on the mission, and each layer actually involves carrying off the mission and also an abort plan as well. So we're multiply backed up. But let's say everything works as it should. We go and land at landing site number 1. We can check out the Earth return vehicle. We've already had automated health checkout on it, but now we can check it out in person. It's fine. We take the second Earth return vehicle and we land it somewhere else. It could be anywhere else, but I like to land it a few hundred kilometers away because it will be the next landing site for the next crew. But if we need it, we could still be able to drive to it. So the crew will have available to them 2 complete Earth return vehicles, either one of which can take them home. But the main purpose of the second Earth return vehicle is to be the return vehicle of the next crew, which will fly there 2 years later along with their Earth return vehicle backup, which otherwise is used to open up landing site number 3. So the idea is every 2 years we launch 2 vehicles to Mars, one to open up a new site, one to exploit the previous site. 2 vehicles every 2 years is an average of 1 per year. When we were launching the space shuttle, we were averaging 6 a year. So this would take 1/6 of our heavy lift capability to do this. So we don't have to just do this and not do anything else. We could do this and do the moon, do asteroids, do space telescopes. We can do lots of things. We don't have to shut down the rest of the space program in order to go to Mars. It can be just a reasonable fraction of the overall heavy lift capability. So next. So here's a artist's conception of the Mars base. And here you see the Earth return vehicle on the right, the tuna can habitat on the left. The reactor is in the crater in the background. We have some solar panels to use as backup power. We also have 2 vehicles, which can also provide backup power. One is the exploration vehicle, the little pressurized rover. Perhaps hard to see over at the far right is the light truck that was used to deploy the reactor. That's an unpressurized vehicle that can be a backup vehicle for the first vehicle. And then in the foreground here, you see an inflatable greenhouse. That is not a mission critical element. That is an experiment in growing crops on Mars, in Martian soil, Martian sunlight, Martian water, Martian gravity, for the benefit of future missions and future bases. Now, we're going to be on Mars for a year and a half. That's the time it will take before it's time to go home. We're going to be exploring on Mars for that period of time. And it makes sense to spend a year and a half on Mars if it takes a year to do the traveling round trip. It doesn't make sense to spend 2 years traveling and 1 month at Mars. That's absurd. So this is rational. But what are we going to explore for? Well, there's all sorts of things people are interested in about Mars. We'll want to know about its minerals, and we want to know about its geology and all these sorts of things. But there's two principal questions that make Mars of interest to everyone who's a thinking person. And the first of these two questions is, was there or is there life on Mars? Okay, now this is a piece of art. This is an actual photograph of Mars taken in 1976 by the Viking orbiter. And what you can see here are dry riverbeds on Mars, lots of them. There are no canals on Mars. That was fantasy. But there are certainly dry riverbeds and many other water erosion features that have been observed all over Mars. Okay, there are dry rivers, there are dry lakes, there's even what looks like the basin of a dried out northern ocean. Okay, and it is apparent from this data that Mars had liquid water on its surface for about 1 billion years during the planet's early history. Now, life appeared on Earth within 200 million years of there being liquid water here. So this is 5 times as long as it took life to appear on Earth after we had liquid water. So if the theory is correct, that life is something that naturally emerges from chemistry, wherever you have liquid water and rocky geology and enough time, then life should have appeared on Mars, even if it subsequently went extinct on the surface when it cooled down and it couldn't have liquid water anymore. So if we can go to Mars and explore and find fossils on the surface, we will have proven really that life is a general phenomenon in the universe. It will have proven that life appears wherever it could. See, right now we don't know. We know life appeared on Earth, but we don't know whether it was a 1 in a million shot or a certainty. But if we find it on 2 out of 2 planets, it means it was a high probability event. And since we now know from the Kepler Space Telescope that most stars have planets, and that at least 1 out of 5 stars has an Earth-sized planet in its habitable zone, that is the right distance for the temperature where you have liquid water. And, there's 400 billion stars in the Milky Way galaxy. 1 in 5 is 80 billion stars with planets in their habitable zone. If life appears on planets where there's a habitable zone, it means there's 80 billion planets with life. And that means there's probably intelligent life all over the place too. It means we're not alone. So that's what we find out by going to Mars. Or if we find out that, yes, we had all these favorable conditions, we had liquid water, lots of time, but no life, that could mean that we're completely alone in the universe, because it could mean that what happened on Earth was a matter of wild chance. But furthermore, while there is no liquid water on the Martian surface today, there is liquid water underground on Mars where it's warmer. Okay? There's a Martian water table, and it's within 1 kilometer of the surface. So if we can go to Mars and drill, we can drill down to where there's liquid water. And if there was ever life on the Martian surface, it would have retreated there. We have microbes in the groundwater of Earth that date back for 3 billion years, that they had to leave the surface of the Earth because oxygen from plants made it intolerable for them. These creatures, microbes, evolved when there was no oxygen in the Earth's atmosphere. When plants put oxygen in the Earth's atmosphere, the surface of the Earth became uninhabitable for them. They went underground. They're still there 3 billion years later. They've seen the trilobites and the dinosaurs and the mammoths come and go. They're still there. If there was ever life on the Martian surface, it's still there underground, and we could reach it by drilling and bringing up water. And if we do, we would not just know that it's life. We could learn about its biochemistry. And this is very interesting, because you see, all Earth life has the same biochemistry. It all uses the same alphabet for transmitting information, RNA, DNA. Okay? Now, I'm an American. I speak English. We use the Latin alphabet. So do you. in the Czech Republic, and the Poles do, and the French do. But not too far away from you, there are people that use the Cyrillic alphabet. Okay? It's a different alphabet. It's not that different, uses the same principles, okay, but it is different. So the Latin alphabet is not the only possible alphabet. Furthermore, if you travel a bit further and go to China, they use an information system that not only doesn't look like ours, it doesn't work on the same set of principles at all. Okay? Our alphabet and the Cyrillic alphabet works by using letters to spell out sounds. Chinese alphabet is based on pictures. And yet you can write books in it. They do. So it's a different information system. So all life on Earth uses the same alphabet, the same information system, but life elsewhere might not. All life needs an information system, but it doesn't have to be the same as ours. And this, in other words, if we could go to Mars and see what information system the life there uses, it could tell us a lot about what is fundamental to life itself and what is accidental, what is just the alphabet that we happen to have. Okay? We use this same Latin alphabet because the countries were once part of the Roman Empire or the Roman Church or something, but other alphabets are possible. Other biological alphabets are probably possible, and other information systems. And you know, first computers, information system worked with gears and levers, and then they had electric relays, and then vacuum tubes, and then more recently silicon. And now there are people working on DNA computers and quantum computers. And each of these new kinds of information systems created new possibilities for cybernetic technology. Well, it could be the same with life. And this can have enormous implications, not only to our understanding of theoretical biology, but to biotechnology as well. So we're going to be on Mars for 1.5 years. At the end of that time, we get in the Earth return vehicle, we fly back to Earth. We leave behind on Mars our habitat and the rest of the base. And after a number of these missions have occurred, and let's say they're spaced out as you see here, we'll have a string of bases on the surface of Mars. And I put here, there's a image of the state of Texas, about as big as France. That's about the area that can be explored in any one of these missions. Okay. And you could drive from one base to the other, which are the centers of these circles. But after a number of these missions have occurred, and I don't know whether it's 8 or 6 or 12, but a certain number, we'll know whether there was ever life on Mars and if it's still there underground, and if so, what chemistry it uses and all of that. And at that point, the key question about Mars is going to shift from the question about was there or is there life on Mars to another question, which is even more important, which is, will there be life on Mars? Because the key thing to understand about Mars is that it's not just an object of scientific interest. It is a world. It's a planet with a surface area equal to all the continents of the Earth put together. And if we can go there and learn how to take the materials there and turn them into resources, then we can make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet, turn it into an entire living world covered with meadows and forests and wildlife and farms and everything? Well, yes, I do. But not immediately. That's a very long-term project. However, what determines what we can do in our time is not so much transform Mars physically into a fully living forested world, but intellectually. Because that is, we can make it habitable intellectually, because what determines whether a place is habitable or not is whether you know how to take the materials there and turn it into resources. You know, our most distant ancestors came from equatorial Africa, from Kenyan Rift Valley. Okay, human beings are actually tropical animals. That's why we have these long, thin arms with no fur. Look, no fur. In our native form, in the state of nature, neither Europe nor North America nor most of Asia was habitable for people. It's too cold. We had to develop technology that allowed us to move into Ice Age Europe and Asia and ultimately the Americas. That it was developing technology like clothing and fire and houses and ways to acquire food all year round, even in the winter, which entailed big game hunting and therefore language to coordinate people and weapons that could kill at a distance. All sorts of things had to be developed before humans could transform themselves from a local tropical species to a global species, okay? And be able to live in all the places we now live, okay? Well, it's the same for Mars. And I would say that Mars today is less of a challenge than Ice Age Europe was to early tropical man, okay? Because we can understand that we have much more science available to us to deal with the problem. So if we can go to Mars and learn how to make not just rocket fuel and oxygen out of the atmosphere, but learn how to grow food on Mars, learn how to make greenhouses to grow food in on Mars, making glass and plastics and metals and motors and wires and tubes and habitation structures. If we can master the craft of turning the materials on Mars into resources, then Mars becomes habitable for us. It becomes a place where new branches of civilization can grow. And until in the fullness of time, they are big enough and strong enough and with industrial capability and technological capability that they can actually address the challenge of transforming Mars itself. Okay, so that ultimately we don't just bring life to Mars, we bring Mars to life. Okay, that's the program. Create new branches of human civilization and new planets for them to live on. I think I'll leave it there, and I'd love to take questions.
Thank you. Thank you, Dr. Zubrin. So now is the time for questions. Is anybody want to ask something?
Is there a question? I couldn't hear it if someone asked a question.
So I would like to ask, in your proposal, you use this very long rope to rotate the spacecraft. And so what do you think about Elon Musk's plan to go to Mars by Starship? And in my mind, there is no plan for artificial gravity, and he plans to send 100 people at a time. So do you have some inside information about this, how to solve artificial gravity?
Can you repeat the essence of the question? Because I couldn't quite make it out. Yeah, he is. Okay. Now, Musk is using the technology of making methane oxygen on Mars for direct return. That is part of his plan. He does not include artificial gravity. Now, that might be viewed as a mistake. there are ways I could think of. If you sent two starships to Mars, you could tether off of each other and spin it up and make artificial gravity. Another viewpoint is that Musk is actually not really concerned so much with exploration as settlement. And if you're going to Mars one way in a starship and, you know, okay, you get weakened in zero gravity for 6 months, but then you take a month to recover while you're on Mars, and then after that, you're fine. But I prefer artificial gravity myself. By the way, let me add something right now before I forget. I'm going to be speaking in Krakow at the AGH University on June 21st. So I know that's not right next door, but it's not an impossible trip. And to get the details of it, you contact the Mars Society Polska. Okay.
Další dotaz je tady z chatu. If there is some life on Mars, is there a risk of bringing it back home? Did you consider the risk?
Was the question about the possibility of back contamination? Okay. Okay, that's a good question, and it's an important one. I don't believe so, and I'll tell you why. Because we have a natural transfer of material from Mars to Earth due to meteoric impact. And we have had for the entire history of the solar system. That is, meteors hit Mars, they knock material off, and that material lands on Earth. And from examination of some of this material, for instance, the Allen Hills meteorite, which came from Mars and was discovered in 1983, and then made headlines in 1996 when a group said they had found evidence of past life from Mars in it. That's controversial. But what is fact is that it was shown that large portions of the Allen Hills meteorite had never been raised above 40 centigrade during its entire history of ejection from Mars, flight through space, and re-entry and landing on Earth, which means if there had been microbes in it when they were on Mars, they could have survived the trip and made it to Earth. And we get kilograms of this material landing on Earth every year right now, and have had for 4 billion years. In fact, we used to have more. So if there could be microbes coming from Mars to Earth, they already have. Okay. Now, chances are, as soon as they landed on Earth, they got eaten by Earth microbes. Because it's like transporting sharks to the African savanna, where sharks are pretty good for living in the ocean, but they're not terribly good for living on land. And so the lions and hyenas get to eat them up. Or if you threw lions into the ocean, the sharks would eat them. It's the wrong environment. Furthermore, even if they could live on Earth, they could not be pathogens. The pathogens that affect humans all evolved along with us or with animals that are really very closely related to us, such as other mammals. People don't get diseases from trees. They're much too distant and different from us. You could get a disease from a dog or bat, but those are mammals. Those are very close relatives. So more distant related organisms like trees, no. And so there's no macroflora or macrofauna of any kind on Mars. And so there could not possibly be pathogens there. And as I said, if there were, they're already here. So I think that the concern over back contamination is misplaced. If you're worried about back contamination, worry about gardeners, because people who dig in their garden bring up sediments from the Earth's past. And the Earth of the past definitely had diseases in it that could affect you. Okay. You could go dig in your garden. You'll bring up dirt from the time of the Black Death. So the Earth of the past was loaded with pathogens. And so gardeners, farmers, construction workers, anybody who digs, is dogs, creating a much greater contamination hazard.
Okay, there is another question from online chat about economic and strategic importance of Mars. If it is not important, so is there a chance that the society on Mars will develop some conflict with Earth, or if there will be conflicts among nations on Earth about Mars? Is there some kind of Martian law already?
Okay, well, wow, that's a big question. And actually, I've written a whole book on the subject, which is going to be published next year. And its title is The New World on Mars, What Can We Create on the Red Planet? And it looks at future Martian society in all dimensions: technological, economic, social, political, aesthetic. And I don't try to design a utopia. Rather, what I try to do is figure out what is likely to emerge. And because I think everything is going to be tried. I think lots of different kinds of people will go to Mars and establish different kinds of city-states based on their own ideals. And the question is, what's likely to succeed? Okay. And for example, I believe that Martian cities will be free. Why do I believe that? Not just because I prefer human liberty, but because I believe it's fundamental to the survival of a Martian city. In other words, I don't think you could have a Martian tyranny succeed because, first of all, no one would want to emigrate there. So a tyranny would not get immigrants, and so it would not grow. But furthermore, I think one of the main, the Martians are going to have to be very innovative. They're going to have to be a nation of inventors to invent the technologies they need to survive. But also those technologies will be among their primary exports. Mars will face a severe labor shortage. So the Martians are going to need to be experts, virtuosos in automation, robotics, artificial intelligence, other labor-saving machinery. Mars is going to have limited agricultural area. They're going to want to be innovators in biotechnology. Mars can't use fossil fuels. They're going to want to innovate in nuclear technology. And these innovations that they make for themselves will be licensable as patents on Earth and be one of their principal sources of income. Once again, you can't have invention without freedom. Not much. So there will be different kinds of Mars city-states, but I think the free ones, the ones that promote freedom and therefore immigration and economic growth, will be the ones that prevail. They'll outgrow the rest. I'm going to have to leave soon. Once again, I am speaking in Krakow at, I think the university is called AGH. And I don't know if you know Mateus is with the Mars Society Polska. I could try to put you in touch with him. He may be able to give you the time and place if you want to come. And also, of course, the Mars Society is having its own convention in Arizona in October. And you can come there. And if you can't come, it will be online as well. You can attend virtually. So how do you say goodbye in Czech? What? Ciao. Okay. Like Italian. Ciao. Okay. All right. Well, thank you.
Thank you very much.
All the best to everyone. Okay, see you in Krakow.
Tak já se loučím i s panem doktorem Zubrinem, loučím se s diváky. Dobré vědět, děkujeme. Následující program ještě uvedeš? Jo?
Já děkuji všem, že přišli na tuto přednášku a ti z vás, kdo ještě nikam nemusí rychle odejít, tak dole v bývalé armě je připraveno malé pouštění, takže tam bude zřejmě další diskuse na téma a na spoustu nezodpovězených otázek, které nám tady doktor Zubrin zanechal. Tak ještě jednou děkuju.